Welcome to the second lecture in thermodynamics. The topics that we will explore in this lecture include potential energy, mechanical energy, and conservative versus non-conservative forces. Okay, so we'll start this lecture with the exercises from the previous lecture. And in the first exercise, a toy car is pushed 0.500 meters by an applied force of 2.40 newtons, while the opposing force of friction is 0.600 newtons. We will determine the work done on the car by the applied force, the work done on the car by friction, and the total work done on the car by the combination of the applied force and friction. Now we can choose our reference frame so that the direction of motion coincides with the positive x-axis, and so our displacement vector is 0.500 times I hat in units of meters. The applied force is 2.40 times I hat in units of newtons, and the force of friction, which opposes the direction of motion, is negative 0.600 times I hat in units of newtons. So the work done on the car by the applied force is the dot product of the applied force and the displacement vector, which is 2.40 times 0.500 in units of joules. And to three significant figures, this is 1.20 joules. The work done on the car by friction is the dot product of the force of friction times the displacement vector, which is negative 0.600 times 0.500 in units of joules, and this is negative 0.300 joules, or negative 3.00 times 10 to the negative first power in units of joules. And so the total work done on the car is the sum of the work done by the applied force and the work done by friction, which to three significant figures is 0.900 joules, or 9.00 times 10 to the negative first joules. Now we could also first determine the total force, which is the sum of the applied force and the force of friction, which is 2.40 minus 0.600 times I hat in units of newtons, which is 1.80 times I hat newtons, so that the total work is the dot product of the total force with the displacement vector, which is 1.80 times 0.500 in units of joules, which to three significant figures is 0.900 joules, or 9.00 times 10 to the negative first joules. Now notice that the magnitude of the total force is the magnitude of the applied force minus the magnitude of the force of friction. And so the total work is the quantity, the magnitude of the applied force minus the magnitude of the force of friction times the magnitude of the displacement. So we have the product, the magnitude of the applied force times the magnitude of the displacement minus the product of the magnitude of the force of friction times the magnitude of the displacement, which is the work done by the applied force plus the work done by the force of friction. Now in the second exercise, a soccer ball of mass 0.420 kilograms is moving with a speed of 6.00 meters per second. If the opposing force of friction is 1.40 newtons, how far will the ball travel before coming to rest, assuming no other interaction with the ball? Now once again, we can choose our reference frame so that the direction of motion coincides with the positive x-axis. And so our displacement vector is some change in the x-coordinate times I hat in units of meters. The force of friction, which opposes the direction of motion, is negative 1.40 times I hat in units of newtons. The initial speed is 6.00 meters per second. The final speed is 0 meters per second. And the mass of the soccer ball is 0.420 kilograms. So using the work energy theorem, we have that the work done by the force of friction is the dot product of the force with the displacement vector, and this is equal to the change in the kinetic energy, which is 1/2 the mass times the quantity, the final speed squared minus the initial speed squared, where the final speed is 0. So on the left-hand side, we have negative 1.40 newtons times delta x. And on the right-hand side, we have negative 1/2 times the mass times the initial speed squared. So delta x is the mass times the initial speed squared divided by 2 times 1.40 newtons. So this is 0.420 kilograms times 6.00 meters per second quantity squared divided by 2 times 1.40 newtons, which to 3 significant figures is 5.40 meters. Now last time we derived the work kinetic energy theorem for a constant force. We will now build on this theorem by considering variable forces, and we will start in one dimension. Okay, so suppose that we have a force that varies with the position x. Then we can choose a very small displacement, delta x, during which time the force is essentially constant. Notice that the area of this rectangle is the height, which is the value of the force at that position, times delta x. And by the work kinetic energy theorem, this is equal to an infinitesimal change in the kinetic energy. So given a start point, x of I, and an end point, x of f, we can divide this area into multiple small displacements during which the force is essentially constant, and take the sum. If we then take the limit as delta x approaches 0, we have the integral from x of I to x of f of x dx, and this is equal to the total kinetic energy change in kinetic energy. Now by the fundamental theorem of calculus, this integral is g of x sub f minus g of x sub I, where the derivative of g of x with respect to x gives us the function f of x. Now g of x sub f is simply the value of the function g at that point, so we'll call it g sub f. Similarly, we'll call g of x of I g sub I, and this is equal to the change in kinetic energy. Now we can rearrange this equation so that we have the final kinetic energy minus g sub f is equal to the initial kinetic energy minus g sub I. Now let u sub x be the negative of g sub x. And then we have that the derivative of u sub x with respect to x is the negative of f of x. And we have that the final kinetic energy plus u sub f is equal to the initial kinetic energy plus u sub I. Now we call this function u sub x the potential energy function, and we call the quantity, the sum of the kinetic energy and the potential energy, the mechanical energy of the system. So notice that potential energy, which we denote with the symbol U, is associated with an object's position. And as we will see, potential energy is stored energy that can be transformed into kinetic energy. The mechanical energy of a system is the sum of its kinetic energy and its potential energy. And as we have seen, at least in the case of one dimension, the mechanical energy of a system is conserved. However, this holds only for conservative forces, and we will discuss conservative versus non-conservative forces in detail. So for conservative forces, the final mechanical energy of a system is equal to the initial mechanical energy of the system. Now, one type of potential energy is gravitational potential energy, which is the energy that an object possesses by virtue of its position in a gravitational field. Now, near the surface of the Earth, the force due to gravity is equal to the negative of the mass times the acceleration due to gravity, where the negative sign is there since the force is always directed towards the surface of the Earth. And so the gravitational potential energy is the mass times the acceleration due to gravity times its position y, the vertical position above the surface of the Earth. Notice that the derivative with respect to y of the gravitational potential energy is the negative of the force of gravity. Now, gravity is a conservative force, as we will see. So if the only force acting is gravity, then the mechanical energy of the system, which is the sum of the kinetic energy and gravitational potential energy, is constant. So let's look at an example. A boy uses a slingshot to shoot a 20-gram pebble straight up with a speed of 25 meters per second. How high does the pebble go? Now, since the only force acting on the pebble once it is launched is gravity, and gravity is a conservative force, the final mechanical energy of the system is equal to the initial mechanical energy of the system. That is, the final kinetic energy plus the final gravitational potential energy is equal to the initial kinetic energy plus the initial gravitational potential energy. And so we have 1/2 the mass times the final speed squared plus the mass times the acceleration due to gravity times the final y position is equal to 1/2 the mass times the initial speed squared plus the mass times the acceleration due to gravity times the initial position y. Now, when the pebble reaches its maximum height, its velocity is 0, and so this term goes to 0. And we can choose our reference frame so that the initial launch position is 0, so this term goes to 0. And so we have the simplified equation, mass times the acceleration due to gravity times the final y position is equal to 1/2 the mass times the initial speed squared. The mass cancels on both sides, solving for the final y position. The final y position is equal to the initial speed squared divided by 2 times the acceleration due to gravity. So this is 25 meters per second quantity squared divided by 2 times the acceleration due to gravity, which is 9.80 meters per second squared. And to two significant figures, this is 32 meters. That is 32 meters above the launch position. Notice that the result does not depend on the mass of the object, as is expected for an object in free fall. So let's focus on a few points from that example. First, the maximum height of the pebble was the square of its initial speed divided by 2 times the acceleration due to gravity. And this is true in general for any projectile in free fall, that is, for any projectile for which the only force acting is the force of gravity. And in the initial state, all of the mechanical energy of the pebble was in the form of kinetic energy, and in the final state, all of the mechanical energy of the pebble was in the form of gravitational potential energy. So the kinetic energy of the pebble was transformed into gravitational potential energy. So what is the speed of the 20-gram pebble when it returns to its initial launch position from its maximum height? Now once again, the only force acting is gravity, and since gravity is a conservative force, the mechanical energy of the system is conserved. And so we have 1/2 the mass times the final speed squared plus the mass times the acceleration due to gravity times the final y position is equal to 1/2 the mass times the initial speed squared plus the mass times the acceleration due to gravity times the initial y position. Now when the object returns to its initial launch position, its final y position is 0. And when the object is at its maximum height, it has 0 speed. So we have a simplified equation. 1/2 the mass times the square of the final speed is equal to the mass times the acceleration due to gravity times the initial y position. Once again, the mass cancels on both sides, and we have that the square of the final speed is 2 times the acceleration due to gravity times the initial height, so that the final speed is the square root of 2 times the acceleration due to gravity times the initial height. And so this is the square root of 2 times 9.8 meters per second squared times 32 meters, which to two significant figures is 25 meters per second. That is, it has the same speed when it returns to its initial launch position as it had upon launch. Now in this case, all of the mechanical energy is initially in the form of potential energy, while in the final state, all of the mechanical energy is in the form of kinetic energy. And so the gravitational potential energy of the pebble was transformed into kinetic energy. Now the mechanical energy of a system is conserved when no forces transfer energy into or out of the system, in which case the sum of the kinetic energy and the potential energy is constant. However, the two forms of mechanical energy, kinetic energy and potential energy, can be transformed from one into the other.